So we're going to review today Chapter 5 on gases. And I'm going to do like I usually do, put the review document on the board or on the screen. And I've got several of them picked out. I've got to be very selective because we don't have much time to get through these. So if the questions in here are just a matter of memorization, you have to know, say you have to know what the gas law is, say Graham's law or Boyle's law, you have to know what it is, then I'm not going to review those. Because I figure rote memory is something you can do on your own. But I will get started with number 5. Okay. A glass column is filled with mercury and inverted in a pool of mercury. Now, I assume when we do this, we don't submerge our hands. We know better now. So you've got a glass column submerged in a pool of mercury. So it's going to be like that. And you've got a column here. All right. I assume it's closed at the top. Yeah. Okay. The mercury column stabilizes at a height of 729 millimeters above the pool. So the distance between here and say here is 729 millimeters. All right, that's what we're given. What's the pressure of the atmosphere? Oh, this is unit conversion. That's it. I didn't need to draw a picture, did I? So what do we need to know? This is simple dimensional analysis. You want to be left with atmospheres, you get rid of cancel millimeters of mercury, so you need to know the relationship between the two. And just 760 into 729 will give you 0.959. Okay. That was too easy. I probably should have skipped that one anyway. But let's consider it a warm-up. All right. Clicker. Too many things in my hand. Okay. Number 12. There it is. Let's see. That gives us the picture, but it doesn't give us the answer. Hold on a second. Scroll a little bit. Probably have to scroll some more. As soon as we get this one identified, what type of problem it is. So relative to this picture, we have a sample of helium gas in this container. It's got a piston that's ideally frictionless, of course. And we have a 10 kilogram mass on top. So there's a constant pressure. How many of the following processes will cause the piston to move away from the base? In other words, volume will increase and the pressure will decrease. Okay, how many of these will do that? We want the conditions where the volume increases and pressure decreases. Okay. All right. Now that we have that in mind, let me scroll down to our choices. There we go. So what happens when we heat the helium? Right? Will the volume increase? Well, yeah. According to Charles, it will. So it meets this condition. How about this condition? What happens to the pressure? Nothing. Because it's under this constant weight right here. Plus atmospheric. Okay, so that doesn't change. So Roman numeral 1 is false. It doesn't satisfy. How about 2? Remove some of the helium from the container. So if we remove some of the helium from the container, what does that say? Well, that's Avogadro's law, right? Remove some of the helium, then the volume decreases. So that won't match either. That one's false. Turn the container on its side. What if we can turn the container on its side? What happens? Now that mass is not bearing down on the gas. It's sitting on its side, right? The force of a mass is perpendicular to the surface of the earth, right? It bears down toward the center of the earth. So if we put it on its side, now that mass is down this way and the gas is over here. So we've decreased the pressure, right? So we met that condition. It's number 3. And what will happen to the volume? Right? That's a constant. So if it's going to be constant, then as the pressure decreases, we didn't change the number of moles, we didn't change the temperature. So pressure volume is Boyle's law. We decrease the pressure, so the volume has to increase. That's a good one. Roman numeral 3. Let's check out 4. Decrease the pressure outside the container. Right? So if we decrease the pressure outside the container, how do you do that? It doesn't say that it's inside a bell jar, but we would have to do that. We'd have to put it inside a bigger container and suck the air out of it. Right? Otherwise, it's always going to be 1 atmosphere in addition to the 10 kilograms. Right? So if we do that, we have decreased the pressure and the volume is going to increase. So 4 also satisfies the conditions. Okay? All right, so the answer for that one is C, which means 2 of them are correct. That's it, you got C. All right. Okay, let's see. What's the next one I got marked up here? About number 15. There it is. 15. Gaseous chlorine is held in 2 separate containers at identical temperature and pressure. Okay. Gaseous chlorine is held in 2 separate containers. Identical temperature and pressure. So the temperature of this one is equal to the temperature of that one. Pressure of this one is equal to the pressure of that one. The volume of container 1 is 1.30 liters. So this is 1.30 liters. And this one is 6.7. I'm going to make this one a little smaller. I'll make this one bigger. This one's 6.7 moles. This one is 2. Okay, that's too big. It's going to be about twice this one. Okay. Now we've got 2.33 liters in this one, and how many moles of gas are in that? That's the question. How do we approach this problem? Is this a before, after, or a state function? Before, after, right? Even though they're separate containers, the conditions are identical. Two temperatures the same, two pressures the same. We have a different volume, therefore the moles have to be different. And it doesn't matter what the gases are. We say it's chlorine, but it really doesn't matter. A gas is a gas under these conditions. So we can say this is the before condition where liters, what's the relationship here? Well, if you can't remember, pressure, volume over moles and temperature. Temperature is constant, right? Pressure is constant, so it's V1 over N1 equals V2 over N2. That's where you can use the combined gas law to figure out which one to use. Because we know the pressure and temperature are constant, that means volume and moles vary. So that's the law we're going to use. By the way, which one is that? Yet again, guy was an Italian. Gaudreau's law. So we have to identify and be sure that we know this is V1, this is N1, this is V2, so that's N2. Because if you don't put them in the right place, you're going to come out with the wrong answer. So sometimes drawing a picture, at the very least, extract the information from the word problem. Right? Get it out of there. Because word problems are designed to confuse. All right, so if we plug in 1.3 liters divided by 6.7 moles, and that's equal to 2.33 liters divided by the unknown. You know, we just solved that. So we pull this one over here, put that one over here, put this one over here, and we get our answer. And in the interest of time, N2 should be 12 moles, I think. 15, yeah, 12 moles. And then you ask yourself, is that reasonable? Well, let's see. We roughly doubled the volume, so we should have twice the moles, right? 6 to 12. Okay, we're in the ballpark. So that answer seems reasonable. Or number 15. All right, let's get down to 18. I'll do that. Yeah, I'm going to have to scroll a little bit. Okay. Body temperature is about 309 K. It's a good thing they said about, because I know for a fact what we take as normal body temperature, 309 K would be what? 309 and 273 minus that would be 36 degrees Celsius. You know what body temperature is in Celsius? You plug 98.6 into that formula for temperature, you're going to come out with 37 degrees exactly. So whoever supplied this temperature for the problem is, at the very least, below normal. And perhaps even heading toward hypothermia. Anyway, that's neither here nor there. The body temperature is 309 K. On a cold day, what volume of air at 276 must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? All right, this looks to me, we've got a temperature here and a temperature here, and a volume here, and the question is what volume? So that's a before and after. We have a temperature and volume relationship. So PV over NT, temperature and volume relationship. The pressure doesn't change. Right? This person's standing outside, and the air pressure, whatever it happens to be, doesn't change. Okay, what does change? Temperature changes, volume changes. How about the number of moles? The number, we have to assume that the moles are going to change. Right. So it's going to be volume temperature relationship, which is Charles' law. So we have this relationship, initial, final. Now we have to decide which one's which. We want to get them together. So I like to make a table. Or a list. So what's the initial volume? Well, as long as you match the volume and temperature, it doesn't matter which one you say is initial. But you do have to get them together, right? So if we say the initial volume is 2.2 liters, under what temperature is that found? Lung capacity of 2.2 liters. That would be at the temperature of the body. This is inside the body, so this has to be 309. Now, the temperature final would be 276. Now, in reality, the final temperature is this one, and the initial temperature is this one. But with this type of ratio, it doesn't matter. We're going to find out what that volume is. All we have to do now is solve for this one right here. So that means VITF over TI will be the answer to our problem. Find volume. Okay, so if we put in 2.2 liters times 276 K divided by 309. Okay. That should be, let's see, 1.97 liters. Does that make sense? If we draw in 1.97 liters at that temperature, it's going to expand as it reaches normal body temperature. So it's going to expand at this temperature to that volume. That makes sense. Okay. All right, that was 18. About 20. And I'm going to scroll that page. Just chop it there. So you're holding two balloons, an orange and a blue balloon. Does the color matter? Probably not. The orange balloon is filled with neon. The blue balloon is filled with argon. Okay? The orange balloon has twice the volume of the blue balloon. Which of the following best represents the mass ratio of neon to argon? Okay, so let's draw a picture. We got the first balloon is orange with neon. Neon, this one's orange. And the second one is blue with argon. What's the relationship of their volume? The orange balloon has twice the volume of the blue balloon. Okay. So the blue balloon is going to be like that with argon. This one's blue. Okay. So the volume of this one, the volume of the neon, is twice the volume of the argon. 2 times the volume. What else do we know about these? Okay, it doesn't tell us in this problem. So here's a case where we have to assume that the temperatures are the same. Okay, temperatures are the same and the pressures are the same. Pressure is easier to rationalize because they're both blown up in atmospheric pressure. So the pressure of this one has to be equal to the pressure of that one. Okay. So the only 2 variables are volume and what else? What does Avogadro say? If these were the same volume, they'd have the same number of moles. But they're not. This one's half the volume of that one. So the number of moles of this one is twice the number of moles of argon. That's what we can say about that. Twice the number of moles here is that one. Okay, now how are we going to get at mass? The mass of the individual atoms, right? If this has twice the number of atoms as that one, then what's the relationship of the mass? Well, let's see. Argon is about 40 mass number. Neon is about 20. So each one of these atoms is about twice as heavy as this one. But we've got twice as many of these as that one. So what does that say about the mass? The mass of neon is equal to the mass of argon. We may have twice as many particles, but these guys weigh half as much as those. So the mass has to be equal. It's 1-to-1 ratio of mass. Is that twist anybody's head around? Now, I think in the work problems, I answer this question mathematically. And while it's true, I mean, it makes a hard problem out of an easy problem, I think. That was 20. Okay, what's next one I got marked is skip on down to 29. 28, 29, here we go. Okay, a gas sample is heated from -20 degrees to 57 degrees, and the volume is increased from 2 liters to 4.5 liters. Okay, this sounds like a before and after situation to me. If the initial pressure is 0.140 atmospheres, what's the final pressure? So this looks like you can use the combined gas law. So we know that these initial conditions are equal to these final conditions. Like that. Now we just have to say, are there any of these that we can eliminate? A gas sample is heated and the volume, blah, 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 pressure changes. We have a trapped gas. The moles are not going to change. That means we can eliminate that variable because it's not a variable. It doesn't change. It's a constant. So now we have our relationship. Now what we have to do is say, what's initial, what's final? Right? To be sure and get these in the right place. So initial pressure. A gas sample is heated from this temperature. Well, let's take them in order. Initial temperature is minus 20 C. Final is 57 C. So this is minus 20 plus 273, right? Final temperature is 57 plus 273. Okay, we got those done. And the volume is increased from 2 liters to 4.5 liters. So the volume initial is 2 liters. And the final is 4.5 liters. Okay? The initial pressure is 0.14 atmospheres. 0.140 atmospheres. There we go. So we've got known, 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 unknown. Solve for the unknown. Just take this value over here, multiply those together. Take this value over here, multiply those together, divide that one into your answer. And you get the final pressure of 0.411 atmospheres. Now we can ask ourselves if that's reasonable. This one be in the neighborhood of 253, right? Okay. Yep, 253. This would be in the neighborhood of 330. Okay. Okay. 5. And if we say a tenth of that would be 20, and then a half again would be 30. 3 actually, 3. Right? A tenth of that would be, no, a tenth of that would be 0.2. And then half again would be 0.3. 0.3 times this. So a tenth of that would be 33. That's about 100 up here, roughly. Down here, we've got 253 times 4.5. Is that right? I did that right. No, I can't do that one in my head. So let me just be sure it's correct. 0.14 times 2 divided by 330, times 330, excuse me. And then divided by 253 and divided by 4.5. Nope, that's wrong. It's this one. See, when I started to make that estimate, I said, that's not going to be anywhere near 0.4. So when we actually do the calculation, it turns out to be 0.08. Okay. What fooled me was I could only see part of this letter. And it looks like a C, but it's not. It's an E. It's a capital E. All right, that was 29. Let's see. Do I want to do 30 also? All right. A sample of oxygen gas has a volume of 1.72 liters at 27 degrees and 800 torr. How many oxygen molecules does it contain? Before, after, or state? This is a state, right? You've only got one value for each of the variables. So that means we have to use the ideal gas equation. And then we have to be sure that our values are correct, right? How do we know our values are correct? Because R is 0.8206 liter atmospheres per mole K. So volume has to be in liters, 1.72, that's good. 1.72 liters. How about pressure? Pressure is 800 torr. That's not atmospheres. So we need 800 divided by 760. That's atmospheres. And then we have moles is our unknown. I should have drawn those up there, shouldn't I? Okay, I can do that again. And then temperature. What's our temperature? 27. Right, that has to be in K. There we go. Now we just solve for this one. And that will give us moles. But is that the answer? Not yet. That's the number of moles for sure. So 800 divided by 760 is this value, 1.0526 times 1.72. Okay, and we divide that by 0.08206 and divide that by, what is this? 300? Yep, 300. And that's 7.35 times 10 to the minus 2. Moles. So how do we find the number of molecules? How many oxygen molecules does it contain? We need a conversion factor, don't we? Anybody remember what that was? Molecule. The definition of the mole, 6.022 times 10 to the 23rd molecules. So I just multiply Avogadro's number times that value. Now I get 4.43 times 10 to the 22nd. Molecules of O2. There it is right there. Okay. Like I said at the very beginning, a whole lot of chemistry is nothing but unit conversions. Except you got to be sure you're abiding by chemistry rules, laws. Then you can do unit conversions to your heart's content. All right, that was 30. Yes, let's go to 37. Here we go. Which conditions of pressure, temperature, and moles are most ideal? Now, when I was introducing this material, I mentioned pressure, correct? I mentioned temperature. I didn't say anything about moles. Right? So we're going to have to logic our way through this one. So we're looking for what are the conditions of pressure, temperature, and moles that are most ideal. What do we mean by ideal? That means the gas molecules have no volume. They're moving really fast. They're far apart. And when they do collide, they don't interact. So we overcome the real situation at low pressure and high temperature, correct? What about moles? If you have lots of moles of gas in there, that means that pushes them closer together, right? That kind of defeats the purpose. So we need lots more space, and you get that by fewer moles. So low numbers of moles would also contribute to ideal behavior. Okay? So the one that satisfies that is, let's see, low P here, 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 high T, no, that one doesn't work. That one's okay, that one's okay. Here it is, low moles. Low P, high T, low N. So that's, E answers that one the best. Let's see, 37 ones, and then we're gonna go skip to. Let's see. 52. Oops. Accidentally pressed the wrong button again. 52. Anybody wonder why 54 is deliberately left blank? When I first made up this set, there were some problems in there. I said, wait a minute, we haven't covered that stuff yet. And I had already made out the word problems by hand for all of these. And I found this one and said, wait, looking back on this. So I wouldn't go back and from this point, rework all the problems so they'd be in consecutive order. I just said, okay, we're going to make that one blank. Okay, 52. The mass of 1.12 liters of gas, Y, at STP is found to be 6.23 grams. The density of the gas is what? So when you have a problem like this, and for many problems actually, start with the end. Once you get to the end of the question, the problem statement, go to the end and work your way backwards. The density of the gas is what? That's the question. So what do you need to know to find density? Mass per unit volume, correct? Do we know any of that stuff yet? Well, the mass is 6.23 grams. That's not going to change, is it? No matter what we do to that gas, it's not going to change. What we need to do is find out what's the volume. So the mass of 1.12 liters of gas at STP is found to be this. What's the density of the gas? Well, that's not as difficult as it looks, is it? Except we need to say, what are the units of measure? Okay, we need these units of measure. Liters and grams. We got liters and grams. Okay, so this isn't as bad as I thought it was going to be. We do have the volume, 1.12 liters. And that should be in the neighborhood of 5 something, 5.56 grams per liter. I think the reason I stopped on this problem, and the next one, as a matter of fact, is STP. Did I ever tell you what STP was? Standard temperature and pressure. Okay, what's standard temperature and pressure for a gas? Pressure is 1 atmosphere. Standard temperature for a gas is 0 degrees Celsius, which would be equal to 273. Okay. Yeah.
Just out of curiosity, when you keep talking about Kelvin, I remember there's at least 2 decimal places afterwards. Do those not matter as much, or like?
Not for us. Yeah. We're rounding off to 3 significant figures. Yeah. I mean, if you want to use them, that's fine. Yeah. But for most of our calculations, 3 significant figures will get the job done. So this is true for gases. But for all other phases and any type of chemical reaction that involves a different phase than gas is 25 degrees. So watch out when they say standard temperature and pressure, say under what conditions. But that's for gas. I think I got 53 marked off too. Yep, 53. Here's another STP. The mass of 1.12 liters of gas Y at STP is found to be 6.23. The molar mass of gas Y is what? This one requires a little more work. So the mass is, we've already determined the density of the gas, right? Maybe we can use that, 5.56 grams per liter. We may not need it. The molar mass of the gas, okay? Molar mass is what? Molecular weight is what, that's always what I do. We need to know the mass, how many moles that represents. Okay, so we have the mass, right? 6.23 grams. We need to know the number of moles. So how do we find the number of moles? Well, we don't need the density. What we need is state function, universal gas constant, universal gas equation, ideal gas equation. So the number of moles then would be, let's see, PV equals nRT, N equals PV over RT. Now we can solve this one like that, or we can combine these two equations and then solve that combination for this, and then plug in all our values. Right? If we do that, we can solve this. We know the pressure, correct? Standard pressure, 1 atmosphere. Volume, 1.12 liters. Gas constant, 0.08-206. Temperature, where was that? Oh, standard temperature, 273. Okay? So we can do it that way. And since I'm already started, I might as well finish it that way too. So pressure is 1 atmosphere. Volume is 1.12 liters, 0.08-206, and then temperature is 273. So the number of moles is going to be 1.12, 0.08-206 by 273. Okay, rounded off, 5.00 times 10 to the minus 2. So we put this up here, because that's moles. Divide that into 6.23. And I get 120, see how many significant figures we got. Rounded up to 3, 125 grams per mole. Okay, there it is right there. That was 53. So what do all these solutions have in common? What's the question? Right. 56. I do want to do 56. We'll scroll down to 56. There we go. Which of the following is the best qualitative, let me read it from here, best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature. So we want to graph them, pressure versus molar mass. So let's see, which one should we put on the y-axis? We're going to change the molar mass by picking a different gas, right? So that means the pressure is going to vary dependently. So we should have a graph with, let's see, does it give a, no, okay, so I'm going to say MW is molar mass and pressure. So that's how we're going to graph it. We need to know what this relationship to that is. Okay, how do we approach this? Well, each of the samples are the same size, right? 1 gram, same mass, I should say, not the same size, same mass, constant volume, constant temperature. Okay, so what do we know about that? Well, we know that PV equals nRT relates these factors of a gas. We also know that what molecular weight is equal to, like, is mass per moles. Okay, we know those. So can we combine these two equations and deduce a relationship between this one and that one? Okay, when you combine 2 or more equations, you look for common variables. So a common variable between this one and that one is what? Moles, right? So if we solve this one for moles, N equals M divided by molecular weight. Then we can substitute that one in here. Okay, we could have gone the other way around, solve this one for moles and stuck it in there. We'll end up in the same place. Kind of like solving simultaneous equations in algebra, right? Where you have 2 equations and 2 unknowns. Okay. So if we plug that in here, what do we get? We get PV equals mass divided by molecular weight, okay, times R times T. Okay, that's our combined equation. So what is not changing in this equation? What is it? Mass is not, right. Mass is not changing. Volume and temperature, none of those are changing. So this one's constant, this one's constant, that one's constant, and this one, by definition, is a constant, right? So they're all constant. Let's put all the constants on one side of the equation and see what we get. So this MRT is over here. Let's put V over there. So if we keep M in the numerator, R in the numerator, T in the numerator, and bring V over here to the denominator, right? What do we got left? We got molecular weight, correct? So molecular weight comes over here from the denominator to the numerator on this side. Pressure times molecular weight. These are not changing. That means that they're equivalent to a constant, correct? Okay, what does that look like? Pressure, when you get a product equal to a constant, this is what you get. A hyperbola. Every time. Just like pressure volume equals a constant, Boyle's law. Pressure molecular weight is a constant. So you get a graph that looks like Boyle's law. And it's inversely proportional. So as the molecular weight goes down, pressure goes up. Correct? So is there anyone in there that looks like that? Close, but no cigar, right? This one right here. But that's a straight line. So none of them are right. I need to change one of them, put a straight line from one, and then maybe change one of these others to a hyperbola. That would be devious, wouldn't it?
Couldn't we just turn the hyperbola into the line graph? Because then you say we could.
Oh, yeah, you have to transform it. Yeah. But then you,
Can only answer this, or?
no, that wouldn't answer the question,
Okay.
because it says pressure versus molar mass. Now, if it said pressure versus the inverse of molar mass, now you're talking straight line. And then this one right here would be it. Right, like we did with Boyle's law, pressure versus inverse of volume gives you a straight line. Pressure versus inverse of molecular weight would also give you a straight line. Yeah, that's true. 56, where am I going next? 61, do I need to do 61? Let's skip 61 for now. We can come back to it if we have time. Let's see. Still got one more day in this week. Okay. Number 80. How about number 80? The reason number 80 is good now because we've already done something like number 80 in that previous problem. So it ought to be fresh in your mind. Here we go. Now the question is defining molar mass as a big M. Okay, so instead of MW now I have to use an M. So that's the molar mass. R is the gas constant, T is the temperature, P is the pressure. Which of the following expressions represents the density of a gas? Okay, so what can we get out of these things? Well, RTP sounds to me like ideal gas equation. We can use that. PV equals nRT. Molar mass. What is that equal to? Molar mass is equal to mass per mole, correct? We're also talking about density. So density equals mass per unit volume. Okay? And it wants an expression for the density of a gas with these conditions. So the density of the gas here, D is going to be on this side, equal to something. Okay? So what if we, let's see. We're going to have to put some equivalent. Let's look at the answers. Is volume anywhere in there? No, volume's not there anywhere. That may take care of itself. So I'm fretting over nothing. How about we combine these two. We head toward the density in that direction. Let's do that. So what do we have in common here? We have moles, correct? Moles is a common variable. So if we solve, I think it'd be simpler to solve this one for moles and stick it in that one. So this one is moles equals mass divided by molar mass. So now we can put this one in here. And this is PV equals M over big M times RT. Okay? Now, what do these have in common? Mass and mass, right? Those two have that in common. So it might be simpler to solve this one for M, D times V, and plug it in here. Right? So PV equals dV over M. Well, actually, RT's out here also. It's in the numerator. Correct? This is a big M. Now we need to solve for that big M, correct? Put that one over here, put these two over there. This is dV RT over PV. And that means that volume disappears. And we're left with molar mass is density times R times T over P. Density equals. Oh, wait a minute. I solved for the wrong one, didn't I? Let's try that again. Go back and read the question. We're solving for density. Yeah, which one represents the density? Okay, so the density stays here. This one comes over here. PVM. And then density stays there. And that bring VRT over here. All right, now, what do we got? So that leaves us with P times molar mass over R times the temperature. Now, which one does that match? PM over RT, that A. A is the answer for that. Okay? There's more than one way to get there. As long as you don't do a substitution that gets rid of density, then you should be good. Combining those three equations, solving for density. You'll eventually get there. Whether we went the route I did or whether you try a different route, you're still solving for density using those three equations. All right, that was 80. I got 15 minutes left. Yep. Let's see. I was going to do 81. Let's come back to 81 if there's time. But 86. 86. 142 milliliter sample of gas is collected over water. Let's see, how do they do that? You have water here, and you have a cylinder here, probably. A graduated cylinder. So it's got volume marks on it. And then you have your reaction vessel over here. And it's producing a gas that goes over here and displaces that water. Right? And that top part up there is filled with a gas now. We started off with this thing full of water. Right? Just like Torricelli's barometer. You fill up this thing and invert it in the water. And now there's nothing up there but water. And maybe a vacuum or a little bit of water vapor. But once we start adding this gas, what does it combine with? It combines with some of that water vapor, right? Because water is, it's not like mercury. Water is volatile. Well, mercury has volatility of its own also, but it's not as much as water. And we collect 142 milliliters sample up here. 142 milliliters. So what's in that? We have both the gas and water vapor. Okay. So the question is, what's the volume of the dry gas at standard temperature and pressure? the volume of the dry gas is related to this and that together. And Dalton says that the pressure of this one plus this one is equal to the total. Right? So if the pressure is 753 torr total, the pressure of the gas subtract the water vapor. And the water vapor is given at that temperature, the pressure of water vapor is 20 torr. Remember, torr is a millimeter of mercury. Same thing. So here we have 733 torr. Okay. What's the volume of the dry gas at STP? Let's see. Do we need, it's number 86. I keep feeling there's a simpler way to answer this. See how I answered it before. It's okay. Now we need to find out what the volume is at STP. Standard temperature and pressure. Our initial temperature is 22 degrees C, which is 295. Standard temperature, our final temperature is going to be 273. So we do have a change in temperature. How about pressure? Well, the initial pressure is 733 torr. At this point, we can ignore the water vapor because these gases behave independently. That's what Dalton said. So they behave independently, so the total pressure is equal to the combination of the two pressures, and you can treat them separately. So the final pressure, is that the question? No, volume. The final pressure is 1 atmosphere, or 760. And the initial volume is 142 milliliters. So the final volume is the question. So we have these three variables, and moles will not vary. So that means Ti equals PF BF TF. Okay, so now we just solve for this one right here. We say the initial pressure times the initial volume here, divided by the initial temperature here, and then times the final temperature here, divided by the final pressure here. And that should give us, I don't know, that looks like a C, but it's probably E. I think it's an E. What am I doing? Initial pressure, 733. Initial volume, 42. Final temperature, the initial temperature is 295, we divide that one, and times the final temperature, 273, and then divided by the final pressure, 760. So I get 127. F equals 127 milliliters. So is that one up there? Nope, it's none of these. Okay,
I had a suspicion. That's not a C, that's really an E. Okay, I got a choice to make. Only got 5 minutes left. Which one do I want to do? Let's see. Yeah, I'm going to come back to that. I may have to keep doing these, and you guys can leave if you have to, because there are several that we need to get to. Yeah, that's what I'm going to do. So I'm just going to keep talking and recording, but I do want to. Next one I'm going to go to is 94. 94. And scroll. How do we solve this problem? We've got these two bulbs of gas connected by a valve. That's what that means right there. One of them is 3 liters and the other one's 2 liters. The one that's 3 liters, excuse me, the 2 liter one is 1.80 atmospheres. At 2 liters. And the 3 liter one, connected with a valve, the 3 liter one is 3 atmospheres. Okay, those are initial conditions. The valve's still closed. So we're going to open the valve. So which way is the gas going to go? Right? High pressure to low pressure until it equalizes. So the final pressure, qualitatively speaking, should be somewhere between 3 and 1.8, right? If you get a value, if you work this problem the way I'm going to show you, you get a value less than 1.8, you know it's wrong. You get a value greater than 3, you know it's wrong. It's got to be between. So that means we can throw this one out immediately. And we can throw that one out, right? Because it's not going to be the same here. So it's either this one, that one, or that one. How do we solve this problem? We use 2 different laws, Boyle's law and Dalton's law of partial pressures. Here's how we do it. Dalton's law says these gases act independently, even if they're the same gas, same formula. They act independently. So if they're going to act independently, why don't we just say, all right, that's a vacuum. There's no gas in there. We'll save it till later. So what happens if that's a vacuum? What pressure does this contribute? Then say this one's a vacuum and let that one go in here. What pressure does it contribute? Then what's the answer? The sum of the 2. They're partial pressures, aren't they? So add them together and you get the final. So how do we get the final pressure for each one? Boyle's law. Right? So on this side, the initial pressure is 3 atmospheres. The initial volume is 3 liters. The final pressure is, who knows? That's the question. And the final volume is what? 5 liters. 3 plus 2. Okay? So for this one, the final pressure is equal to 9 divided by 5. 9/5 atmosphere. Okay? Now let's make this one a vacuum. See what happens with that. Right?
Okay, initial pressure is 1.8 atmospheres. Initial volume is 2 liters. How about the final volume? It's the same, it's 5. Okay, so this one now is going to be 1.8 times 2, which is 3.6 divided by 5. So this one is 3.6 divided by 5. And the total pressure is equal to 9/5 plus 3.6 divided by 5. Which they've got a common denominator, so we just add 9 and 3.6, right? 12.6 divided by 5. 12.6 divided by 5. So I can't do that one in my head, and we got 3 choices in there that are really close together, so let's just calculate. 2.52. So the final pressure is 2.52 atmospheres. Okay. There we use 2 gas laws to solve this problem. Okay, let's see. 95. Ooh, went to scroll. 95. The partial pressures of methane, nitrogen, and oxygen gases were found to be 135. Oh, that was chopped off of me. 508, 135, 508, and 571 millimeters of mercury. Let's see, this one was for methane, nitrogen, and oxygen in a mixture. Calculate the mole fraction of nitrogen. Okay, what do we know about this problem is that the conditions are the same except for the different pressures of the gases. We have to assume that the temperature is constant, the pressure is constant, the total pressure is constant. The moles vary for these right here, but the total moles doesn't change. See, pressure, volume, moles, pressure, volume, moles, temperature doesn't change either. So the important thing to remember here is that the mole fraction is proportional not only to the moles of a gas, a fraction of the moles in the total, but all other things being equal, it's also proportional to the pressure. We looked at that with Dalton's partial pressure, right? Where we said the total pressure is equal to, let's see, if PV equals nRT, then pressure equals nRT over V. Remember that series? If this is total, then it's composed of these 3 gases, right? Same temperature, same volume, right? So all of these cancel out, and now the pressure is proportional to the number of moles of each one. These represent the pressures of each one of those gases. And since these don't change, then the pressure is proportional to the moles. So if we do the mole fraction of nitrogen, actually the moles of nitrogen over the total moles is the same as the pressure of nitrogen over the total pressure. Okay, so all we have to do is say, divide this one by the total, right? And that'll give you C. That is a C, 0.418. Is that reasonable? Yeah, pretty good. this plus this plus this, divided into that. That's less than half. So I think that's, well, we'd have to calculate it exactly, but it's 0.418 is the molar fraction. All right. Let's see.
103 requires that you calculate the root mean square velocity for oxygen molecules in a sample at 11.8 degrees C. 103.
Here we go. So 103 wants to know the root mean square velocity. Remember the formula for that? It's in your useful information. It's the square root of 3 over RT divided by the molar mass. So what's the molar mass of oxygen? It's 32 grams per mole. But remember, R has buried within it kilograms. So we got to change this one from grams to kilograms. So which way does the decimal move? Goes to the left, right? 3. So this is actually 0.032 kilograms per mole. Now that one goes right here. And this R is 8.3145. And the temperature has to be in Kelvin, so 11.8 plus 273. Right? For these two, right above that one times 3, square root, and you got your answer. Which for 103 is C. C, here we go. 471 meters per second is the root mean square velocity of oxygen at this temperature. Okay? That's the trick right there. Don't forget to change that to kilograms per mole. If I were devious, I'd say, what if you put in 32 here? It would decrease this, right? By 1,000. Right? Divide it in there by 1,000 too big. Then I would decrease that by 1,000. So I'd say root mean square velocity would be 0.471. I put that in there as a selection. And if you forget to change that, you'll think that's the right answer. But I'd do something like that. 103.
Okay, let's go. Let's see. Cover all our bases here. Kinetic molecular theory, Graham's law. We don't need to stop on those. Those are memorization. Let's see. What about 117?
Yeah, if it's got all of them right here, he's the last one. Okay, 117. Order the following in increasing rate of effusion. So what do we know about rate of effusion? Well, the rate of effusion is proportional to the root mean square velocity, correct? The rate of effusion is proportional to that value. Okay, so if it's proportional to this value, it's inversely proportional to the molar mass. That means the smaller molecules are going to move faster. They have a higher rate of effusion. So we just need to find out what is the molar mass of each one of these. Chlorine, chlorine, nitrogen monoxide, nitrogen dioxide, and methane. So we probably don't need to be exact. Fluorine's what? I think it's 19 each, so that's 38. Chlorine's 35, 45. Two of those is about 70. Nitrogen's 14, oxygen 16, which is what, 30, roughly. Then two oxygens would be 32 plus 14 would be 46. And this would be 12 plus 4 is 16. Okay. So the fastest one, the rate of diffusion, the fastest one is methane. So it's going to be rate of diffusion order, increasing order means it'll be on the far right. So it could be this one or it could be that. Let's look at the other end. What's the slowest one? Chlorine, right? Chlorine's the slowest one. So if we got methane choice here, chlorine's here, has to be A. And you can check the others and find that they are in proper order. Okay?
And fusion means, so what's the fusion mean again?
Rate of diffusion?
Yeah.
It's the movement of a gas.
Like how fast it's going?
Yeah, actually, diffusion is how fast does it move from one place to the other in terms of filling space. You can define it in several different ways. One is how fast will it move through a porous screen? But it's all based upon this velocity.
And the highest numbers came from lowest because it was inwards.
Right. They're inversely proportional.
Okay.
Yeah. The big ones move slower. And at the same temperature, they all have the same kinetic energy. Right? But they're moving at different velocities. And that's based on the equation. Right? If it weighs more, it's got to move faster. It's got to move less. It's got to move slower to have the same kinetic energy as its neighbors. All right. Is that 117? Let's look at 124. 124. Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attraction? Okay, in order to answer this question, what he's saying is, if it has the lowest correction factor, means which one is the most closest to ideal. You think about what is an ideal gas. An ideal gas requires that the molecules are small. The molecules are very far apart. So, well, all of them will be that way. They're small and they're balanced. And the chemical term for that is they're non-polar. Polar molecules tend to interact because they tend to be slightly negative on one side and slightly positive on the other. That means when they get close to one another, there's electrostatic attraction. So they have to be balanced in their electron distribution. So something like ammonia wouldn't work. Ammonia is polar because of its, well, we haven't talked about this yet, I don't think. Its shape, and it's two lone pairs up here. So it's going to be polar in that direction, which means it's going to have the strongest attraction. So definitely that one's out. The other diatomics, hydrogen, chlorine, oxygen, they're balanced because they're equal to one another. They pull equally on the electrons, right? So they're all non-polar. So now we look for size. What's the smallest one? Hydrogen. It's just 2 protons and 2 electrons. So hydrogen would give you the most ideal behavior. And an indication of its ideal behavior is it stays a gas until it gets really, really cold. It's down around like 4 Kelvin. I mean, it's almost absolute zero. That means there's no attraction, no significant attraction between the molecules to hold them together. That's what makes a liquid when you compress a gas. Okay, 124. Let's see. How about 142? We haven't done too much with reactions. 142. Reaction between ethane and oxygen. To produce carbon dioxide and water. Let's see, are we going to need a balanced equation here? What volume of carbon dioxide will be produced at standard temperature and pressure from the reaction of 4 liters of ethane and 7 liters of oxygen? I think we do need a balanced equation here. We're going to talk about a reaction. So let's make it quick and dirty. Carbon, hydrogen, oxygen. We have 2 carbons, 6 hydrogens, 2 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay? Let's say we're going to hold this one out for now. 2 carbons, which changes it to 4, 5 oxygens. Okay? Now we balance the hydrogens. So we need 6 hydrogens over here. Right? That's 6 hydrogens. Yep. And that makes 3 plus 4 is 7 oxygens. Okay. How do we get 7 oxygens out of it? Out of a 2 fraction. 7 halves. Okay. So now it's balanced. Well, what we want to do is make whole numbers now. So to get rid of that half, we need to multiply by 2. That makes 2 here, 7 here, 4 here, and a 6 here. There we go. So now we're balanced. Now what do we get? Let's see. Standard temperature and pressure, reaction of 4 liters of ethane and 7 liters of oxygen. So we have 4 liters here and 7 liters here. Okay. And what have I said about reactions when you're given absolute amounts of reactants? One of them is limited. One of them is going to run out. We got to find out which one runs out and what volume of carbon dioxide will be produced. So we're aiming for this one. How many liters of carbon dioxide? Okay, what else have I said about these equations? You can't move anywhere in those equations unless you know moles. But fortunately, we already know that for gases, the moles are proportional to the volume. As long as all other factors are constant, and they are at standard temperature and pressure. So we can treat these like moles, right? I mean, that's not exactly how many moles of this there are, but we can use it as if it were. So if we say 4 liters of this would make how much carbon dioxide? 4 liters of C2H6. And what's our conversion factor? 2 of these for every 4 of those. Right? coefficients. So that means 16 times 8. This would potentially give us 8 liters of carbon dioxide if all of the ethane were used up. How about oxygen? 7 liters of oxygen. Okay. And the conversion here is oxygen to carbon dioxide. Oxygen is 7 coefficient and 4 CO2. So 7 times 7 is 1 and 1 times 4 is 4. 4 liters of carbon dioxide are the most that can be produced from this reaction. That's because oxygen is limiting, right? The least amount that is identifies the limiting reagent. It produces 4 liters. So that means our answer is C. Okay. Looks more difficult than it is. 142. And let's see. 2. Oh, so that's the end. If I back up, see if I missed anything that might be useful. We didn't do any we did a little stoichiometry there. I was looking for another stoichiometry problem. Here we go. Number 81 is a stoichiometry problem. Let's do 81 and see where that leads us. 81, so I can go backwards. Oops, too far. Scroll time. There we go. So this is a problem where we have an unknown metal reacting with carbon, an unknown metal oxide, reacting with carbon to give us the purified metal and carbon dioxide. This is a common reaction that's performed in smelting operations. So we have 2, and we're given the balanced equation. Carbon yields 2 moles of metal and 1 carbon dioxide. Okay, if 34.8 grams of metal oxide, 0.08 grams of metal oxide react with excess carbon. Okay. There's no limit on the carbon. And 4.37 liters of CO2 is formed. 4.37 liters carbon dioxide at 100 degrees C and 1.5 atmospheres. What's the identity of the metal? How do we tell the identity of the metal? Well, we don't know the number of protons, and there's no way to find it. So we're going to have to go with molar mass. So if we can find the molar mass, then we can look along here at these values and perhaps identify what it is. Okay, so the molar mass is equal to the mass or moles. We got the mass right here. Oh, no, we don't. We need the mass of this, right? How many grams of that? And how many moles of that? So how can we get at the moles? Well, we've got a gas here with these conditions, right? Pressure, temperature, volume. We can use PV equals nRT to find the number of moles of CO2, and then use stoichiometry to find out how many moles of N there are. So let's see. N equals PV over RT. Yeah. Okay. So the pressure is 1.5 atmospheres. The volume is 4.37 liters. R is 0.08206. And temperature is 100 plus 273 is 373 K. That'll give us the number of moles of carbon dioxide. 4.5, 4.37, 08206 divided into it, 373 divided. So did I do that right? We do it again. 7 times 0.82. Yeah. 0.214. 0.2142 moles of CO2. How many moles of metal are there? Twice that many, right? 1 to 2. So that means we have 0.4284 moles of metal. Okay, now we got the moles. Now we need to figure out what's the mass. Well, let's see. We know this much here. Can we tell how much of this? That's the long way around. We could do it that way. I mean, we could determine what mass is represented here because we know the moles. And then we can tell what mass is used, what moles is used here, and convert it to mass. And that will give us the total here. And we have this amount, and Lavoisier says that the total on both sides have to be equal. So this minus that would be this. That would work. But I'm pretty sure there's a simpler way. Yeah. Okay, I like that way better. What if we could determine the molar mass of this one, right? Molar mass of this would be that plus that, correct? So for the total molar mass, and we could subtract 16 from that one, and that would give us the molar mass of the M. Let's do that way. Okay, so let's see. How many moles of this do we have? Actually, the same as this one. 2, 2. So this is the number of moles of that. So the molecular weight of MO, molecular weight of MO equals 34.08 divided by 0.4284. That's 79.55. 79. Right? Is grams per mole of MO. So, and that is this one, molecular weight of the metal plus the molecular weight of oxygen is equal to that. So this one is equal to 79.55 minus 16. $63.6. Okay. Now we have to identify the metal. That's where we were headed in the first place. 63.6, is it? Here we go. Closest one, 63.55, is copper. There we go. There for a moment, I was thinking I was going to do it the hard way. All right, let's see.
If I got any others that we skipped and I'll go back to. That covers most of our bases, I believe. We didn't do any of these short answer problems. There's on page 28. But those are fairly well worked out and useful information. I mean, the worked problems. So I think we can leave those. If you have any questions about that, just give me a ring.
Just out of curiosity about this problem.
Yeah.
I was gonna say, where did the 4.28 form, you were trying to get the molecular weight of M of the metal, oxygen? When you were trying to find the molecular weight of the metal and the oxygen by 34.08 by I believe it was
4.4.
4.4.
Yeah.
And what was that from exactly?
I'm sorry.
I said, what was that from? The 0.4.
Oh, we determined based on this information here
Yeah.
that carbon dioxide was 0.2 something moles.
0.0214.
Yeah.
Moles? Yeah.
And the ratio of this one 1 to 2 means that this one has to be 0.4.
Okay, all right.
And this one is 2 to 2. It's the same, MO is the same number of moles. So that's where I got the number of moles for that calculation.
All right.
All righty. I guess we're done. Let's see. Did I miss anybody? I don't think so. Haley's still absent. All right. Okay, we'll see you next Tuesday. We'll do an exam. And let's see. We don't have a lab then, do we? Oh. You don't think we do you? No. Looking at the wrong one. Just to be sure. Right, that's a lab-free day. So I'll hand out on that day, be sure when you take the exam, be sure and pick up a copy of calorimetry. That'll be the lab for that Thursday. Okay, we're done.